Hi there. It is so good to be here. It's so good to have you here. My India ink is in here, and I keep it sealed so it doesn't dry up. But get it opened up for my calligraphy work. So, I was thinking about what to talk about today. And since I know it's the beginning of the semester, for many colleges, beginning of the school year, for many schools in the United States and other places. And depending on where you go to school, there are different approaches to how to begin the school year. And one of the approaches is to start talking about chemical reactions and formulas and doing stoichiometry, the nature of matter. Another way, though, is called atoms first. And with atoms first, you begin talking about the structure of the atom, and eventually you build up to the whole periodic table. And one of the parts of building up to the periodic table is talking about electron configuration. I love how electron configuration is tied in with the whole structure of the periodic table itself. So many of these concepts I have talked about in other videos on this channel. I've talked about quantum numbers and orbitals. I've also talked about what I just mentioned about electron configurations predicting the periodic table. But one thing I have not mentioned, at least that I remember, are the exceptions to electron configurations, and also some of the predictions that you can make about whether electrons are more likely to be gained or lost, and how many you would predict to be gained or lost to give you specific ions based on the electron configurations. So, why don't we start out with this general idea of our electron. And I want to make sure I'm writing large enough. Also, I wanted to let all of you know that I don't just do ASMR chemistry on YouTube, but I also do it on Twitch, on my channel there. So my channel on Twitch is called Chemistry Rockstar, and I don't always do ASMR. I also just teach kind of a regular style, and we have like chemistry study nights, and I'm there to answer questions. Ooh. I'm just winging this here. So if you ever want to just hang out and have me available live, since Twitch is a live streaming platform, that gives you a chance to ask questions in real time. Which I love doing. It's always fun to, just get something thrown at me and work through the problems with you. I also love a challenge, so I'm always like, hey, see if you can ask me a question I don't know the answer to. It's always kind of fun. Okay, and I'm going to add in these exceptions. So let's start out with just some nice review, all right? It's always good to, go back to the basics and go, okay, what are we talking about with electron configurations, right? So, very favorite thing is to always just start at the very beginning. Say we're going to write out the electron configuration for hydrogen. And so we are giving the principal quantum number and the orbital in which we have the electrons. Hydrogen atom only has one electron, so we place it into the 1s orbital. This is the ground state, the most stable configuration of hydrogen. So that superscript 1 is telling us that's where it is. That is that 1 electron. So electron configurations, they are a very nice way to keep track of those electrons. And unless you are told otherwise, we presume that it is the ground state. It is the most stable configuration for that element. Okay, so let's look ahead. And let's look at another element. Let's get a little bit bigger here. And for example, we could look at nitrogen. Okay. And as a reminder here, these, what I see as kind of a periwinkle or a light blue color. This is called the S block, where we are filling the S orbitals. And if we're, say, in period 2, going across like this is now the P block. We are filling the P orbitals. So this is how the periodic table is so handy, is that we see in period 1, we are filling the 1s orbital. You could think of helium as being right here, because truly it does have just 2 electrons in that orbital. But convention is, it is over on this side to be shown in the same group as all of the noble gases. It's a gas, and it does have its orbital completely filled, although it is not an octet. The rest of these have an octet in their outermost orbital. Helium cannot hold 8, so it can only hold 2. A duet, as some people say. So that's kind of a little exception there. But in any case, what we can say is, 1s orbital is being filled, and then immediately thereafter, we would expect the 2s orbital to be filled, followed by the 2p orbital, which is then followed by the 3s, which is then followed by the 3p. Now, there are 3d orbitals that will follow, but the 4s orbitals are actually lower in energy than the 3d. So, in terms of orbital filling, the 4s will be filled first. Okay, so that's the general idea. And as I said, I did go through this concept in an earlier video, another video on this channel. So what I want to do is then looking back at nitrogen. When I say looking back, I just mean I just mentioned it a moment ago. So if we do look at nitrogen and we think about what we just said, that we would say, okay, 1s orbital is filled, so 1s2. Then after that, 2s2. So we have just filled 1s2, 2s2, and now we're filling the 2p orbitals. And we can just count 1, 2, 3. That tells us how many electrons that there are in the 2p orbitals. And we land on nitrogen, which is our element of interest, right? And there are 3 of those electrons that are there. Okay. So, as we go through various examples, and everything is as we would expect. As we go through nitrogen, and then let's say we go to the third period. Let's look at chlorine, for example. So now we filled all the way through neon, and then we start over here, the 3s orbitals. Okay, so a shorthand notation that we can use is, instead of writing out 1s, well here, first let me write this for chlorine. Okay, instead of writing out 1s2, 2s2, 2p6, which would be the electron configuration for neon, we could just write this bracketed notation as such. This is the same thing as if we did write out those 10 electrons that exist in neon. But look how handy this is. All we had to do is write neon, and then we can go to the next shell and begin filling those valence electrons. So for chlorine, the 3s are filled, so there's 2 of them. 3p has how many? 1, 2, 3, 4, 5. Okay. So these are known as the core electrons. Any of those that are part of that noble gas shorthand notation. All of these are the valence electrons. This is where all the fun chemistry happens. This is where electrons are lost, and electrons are gained, and electrons are shared on this realm. Okay. So now, let us take a look at chromium. So, see, we're getting larger and larger. I did an example of hydrogen, then nitrogen, chlorine. Now we're going to hop ahead to chromium. So this is element 24. And we can again take advantage of writing out the noble gas configuration by showing argon. All those are filled. Okay. And then we can begin the 4s and the 3d. Okay. So, chromium. Let's get started. I'll write a little bit bigger here. Alright, so we've got our noble gas, shorthand, argon. Alright, and then we show the 4s. And if we follow the pattern that we've been seeing so far, we would do this. We would write 4s2, and then we would perhaps check our periodic table again, and we would count. For the 3d, this is the d block now, 3d orbitals getting filled. 3d orbitals are getting filled, I should say. There's 5 of them. 1, 2, 3, 4 is what we would write. Now, keep in mind, I'm about to show you why this is incorrect. Okay, so if you're worried, like, wait, this isn't what I was expecting, then don't worry. Or perhaps you're saying, wait, this is what I was expecting. Why is this incorrect? Okay. So this is the deal. Alright. So let's take a moment and let's think about the d orbitals. There are, as I said, there are 5 of them. And if we follow Hund's rule, we would be distributing these electrons as follows. We would separate them all out, spin up. Electrons are slightly more stable than spin down, so those always get filled first. They are in separate orbitals, because then that reduces the electron repulsion, which is a fairly strong force. Those are called Pauli forces when 2 electrons are in the same orbital together. They do that, but if they can separate, if that makes it more stable, they do. Now, here is one other aspect to electrons being in d orbitals, and that is it is more stable for the d orbitals, when possible, for them to be half full. And when I say when possible, it means that it is possible for an electron from the 4s orbitals to move into the d orbitals to achieve that goal of being more stable. And that is exactly what happens with chromium. So as a result, one of these electrons, I'm going to cross this out, one of the electrons from the 4s orbital is actually in the 3d orbitals, and it looks like this. This has an inherent stability that the 3d4 configuration did not have. So the electron configuration for chromium, this is elemental chromium, 0 oxidation state, okay, ends up having 5d electrons. So you may recall that down a group, electron configurations in the valence shell are the same as you go down a group. And so, indeed, molybdenum has this same exception. Tungsten has this same exception. Okay, so we could do the same with either of those. In other words, I'll just show you molybdenum's. Molybdenum is such a fun word to say. A little bit challenging, right? One of those say that 5 times fast kind of thing. Molybdenum. Okay, so the noble gas shorthand for molybdenum, we're starting out with krypton. And then it's the 5s. 1. Now it's 4d. 5. Okay. All right, let's look at another exception. We're going to stay in the transition metals, all right, and we're going to take a look at copper. All right, so copper, just a few more electrons down from chromium. If we count across, 1, 2, 3, 4, 5, 6, 7, 8, 9. So once again, we would predict that our copper, again, elemental copper, would be argon with our 4s2. I'm gonna not even put it there. I'm just gonna start out with what it actually is. We would presume, if we didn't know better, that it would be 4s2. But what happens is, instead of being 3d9, once again, similar kind of reasons, d orbitals, when possible, if they can, have an electron come from the s to completely fill those d orbitals. That will happen. And indeed, that is what happens for copper. So just like with the half full example with chromium, our copper can then achieve full d orbitals if one of those 4s orbitals, for s electrons, if one of them comes over and completes that fullness of the 10. And as you might now guess, silver does the same, and gold does the same. Okay. Now, let us move into the realm of F electrons, of our F orbitals. Okay. And so this means that we could either be writing out electron configurations for lanthanides here, or for actinides here, or for any of the elements that follow the lanthanides or the actinides, which would include lutetium, hafnium, any of these, because the lanthanides are essentially inserted right in here, and the actinides come right in here, right after radium. And the way you can tell this, let's see if I can get a little bit closer and maintain the focus. Barium is element 56. Lutetium is element 71. Okay, so there's been a jump that occurs there. Okay, barium 56, followed by lanthanum 57, and then cerium 58, and it goes on from there. Okay, and by the time we get to the end of the lanthanides, ytterbium is 70, and then it follows with lutetium 71. Same with radium is element 88. Actinium is 89. All the way to nobelium 102, followed by lawrencium 103. Okay. But it can make for a little bit slightly more complicated electron configurations if you are writing it out for any of these. Okay. So how about lead? Let's look at lead, because lead will follow the lanthanides. So we'll see an example there of one of these where we really have to watch what we're doing as we do this kind of electron configuration. Okay, so this is how I always start. I first identify the element for which I want to write the electron configuration. And then I go all the way back and I look at the noble gas that precedes it. Okay, in this case it is xenon. And right away, here, let me draw a line here. Let's start over with a new example for lead. Okay. Alright, so here's our lead. I sort of wrote it like almost like a B flat in music, huh? Kind of did that on purpose. Okay, so here's our lead. And as I said, we'll look at the previous noble gas, xenon. And now job is to march through all of the relevant electrons that follow. So here's xenon element 54. So we come over to cesium element 55. Now we want to be sure. We know that this is the S block, but we want to be sure that we use the correct principal quantum number. Now on my periodic table, there's a 6 there. And that is the principal quantum number for the S orbital here. If your periodic table does not have that 6 there, you can just count from hydrogen. 1, 2, 3, 4, 5, 6. Okay, so there's our 6 S2. All right. Next on the docket, what do we have? Okay, so we have just filled this, and now we jump to the lanthanides, right? So it is very tempting to now immediately, these are the F orbitals, and the very first F orbital that exists are the 4F. Just as a reminder, the very first S orbitals that exist are 1s. The first p orbitals that exist are 2p. The first d orbitals that exist are 3d. So it follows that the first f orbitals are 4f. So, as I said, it is so very tempting to immediately say, all right, this is my 4f orbitals, and fill those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Now, this is the weird thing. Is that what actually happens is there is one electron that goes into the D. Oh, I'm sorry, I need to show better here. Okay. There is one electron that goes into the D orbital. Which D orbital is this? There's the 3D, there's the 4D, there's the 5D. It goes into there first, just one. Then we fill all these, and then it goes back and it fills the rest of them. Wow, what a pain. Okay, but the good news is, because all of these are filled and all of these are filled for lead, we get to just immediately say, oh, thank goodness, I'm just going to put in my 4f electrons. We just counted them up. There's 14, which makes sense because there are 7 f orbitals and they're all full. There's 14 of them. Then we fill the, remember it's 3D, 4D, 5D. So these are the 5D orbitals. 5D. Those are 100% full. So 5D10. Make sure I'm not covering that up. And then what? Here's lead. Okay, so now we're in the P block. Which one is this? Well, the P block is in line with the principal quantum number for the S block. These are always going to be the same. But if you're feeling unsure, you can always count, knowing that the 2p orbitals start with boron. So 2p, 3p, 4p, 5p, 6p. Okay. So we're now at 6p. And there are 2 of them. Okay. 1, 2. And there's our lead. Whew. All right. So we definitely have a lot more electrons to worry about with an example like lead than we do with even over here with something like our chromium or molybdenum. Although with these we need to worry about those exceptions, right? Okay. So the next thing I wanted to mention has to do with ions. All right. And when you're writing electron configurations for ions, you can't just go straight by where it is on the periodic table like you can with the elements, because now you need to think about, okay, how many electrons were gained or how many were lost. Now, the good thing with a lot of these nonmetals over here, or the metals that are over here in groups 1 and 2, is that you often end up with an electron configuration that is the same as a noble gas. So that's something that's very typical. So if you look at, for example, we looked at chlorine over here. So if we look at chloride, we'll be adding an electron, right? So if we already figured out what it was over here, we can see that the electron configuration will be what it was over here, neon, 3s2, but now it's 3p6, and this whole electron configuration is the same as that of argon. So that's a nice example of one of these ions that is the same as a noble gas. Okay, but now I want to show you what happens with something like chromium. And there's a couple common ions of chromium, but chromium plus 2 is one of them. All right, so this is something that if you work with transition metals very often, this is an exception that you can rely on, and that is that electrons in the s orbitals these are always, I love it when it's always and there aren't exceptions, lost first. This is for transition metals. So once those electrons in the s orbitals are lost, then you can start taking from the d orbitals. So in the case of chromium then, chromium plus 2, we can look over here and say, okay, what was chromium, just neutral chromium metal? Electron configuration was 4s1 3d5. So, based on this rule here, we can then say, all right, that means that that 4s electron gets lost first, and then an electron from the d orbital is lost, and ultimately you're left with 4 electrons in the d orbitals, the 3d orbitals. Okay, so here's our electron configuration for chromium plus 2. Let's look at chromium plus 3. Once again, we would have the argon, all the chemistry is happening in the valence shell. That electron in the 4s orbital is lost first, so that's gone. And the other 2 electrons are lost from the 3d, which then leaves behind 3 electrons in the 3d orbital. Okay. And this is seen for all transition metals. You can count on that. Okay. So, like in our molybdenum example, now it would be, and I can just show you that here. That molybdenum plus 2. And by the way, whether you write plus 2 or 2 plus, it's just a matter of preference. It doesn't mean anything different. That's the same thing. So molybdenum 2 plus would be analogous to what we saw for chromium 2 plus. But it would be krypton, and then we would be left behind with 4 of the 4d electrons. Okay. Another thing I wanted to mention, sometimes you'll see in textbooks the order here might be different. The reason why the order is different is because some textbooks, they put them in this order, which is the order of filling, essentially. But some of them put them in the order of energetically, which ones are most stable or least stable. And so you might see the 4f orbitals listed first, and then the 5d, followed by the 6s. So there might be a little bit different order. In my opinion, you can list them in whichever order you want, as long as they are all there. But I would just keep in mind, if you have a teacher that requires them in a specific order, to understand what it is that your teacher wants and why, and be clear on that. Hopefully they don't mark you down for having them in the wrong order. I think it's great to just get all the electrons electrons in there, personally. It's a whole nother level to fully get into the depths of which ones are more stable and why they're more stable. That is all tied in with effective nuclear charge, and it is something that you do learn in upper division chemistry courses usually, some lower division. It just, again, depends on your professor and how they're teaching these concepts to you. Alright, well, I hope that was helpful for you if you're working on electron configurations and maybe doing some examples like this that are delving into realms that we haven't talked about so far on this channel. And as always, please let me know how this is helping you. If you have requests of topics, I love hearing about those. And please share this channel with anyone you think it could help. I have gotten such fabulous feedback on how this kind of teaching helps people learn in just a very relaxed environment. And so I hope it's helping you, and it's just it's really a joy for me to teach in this way. And again, I wanted to invite you to check out my Twitch channel, where I do sometimes teach ASMR style. I tend to do that more often, like at night, where I'm just hanging out. But sometimes I do it as a kind of special live stream that I'm doing for people. But yeah. So thank you for joining me. I'm just kind of doodling here, that's all. Thank you for joining me. And speaking of joining, you can actually join this channel, and that helps support me and my creations here and in other places where I'm just trying to help teach in various ways chemistry online, and give people like you resources that you can use that will hopefully help you with homework, exams, or just falling asleep. Alright, well, have a wonderful rest of your day or evening, and I will see you again next time.